So hello everyone, welcome. As he said, my name's Kyle Pucci and I'm from ImageXpert, and I'll be doing the talk on ink and waveform performance optimization. Before we begin, ImageXpert's the company I work for. We're familiar because we've worked with many of you here, and we just wanted to take an opportunity to say thank you. We really appreciate over the last 25 years working with all of you. It's been fantastic. And we look forward to continuing to work with you in the future. For those of you who haven't worked with us in the past, ImageXpert, what we make are turnkey inkjet development systems. What that means is whether you're developing ink, print heads, or printers, we make the dropwatchers, ink supplies, drive electronics, sample printers, all in one system to help you along the way. So it wouldn't be a talk about waveform optimization without first explaining what a waveform is. So in basic terms, the waveform is the electrical signal being sent to each individual nozzle of the print head, causing them to jet, as you know. Here's the schematic for it. So for most print heads, when a voltage is applied and not applied, it causes the nozzles to move. And waveform optimization is about figuring out the right amplitude and timing to make these changes electronically in order to jet the drops properly. The three basic waveform parameters that I'm going to talk about today are the voltage, which is the amplitude of each given pulse. And depending on the print head, it might be a positive amplitude or it might be going from some high voltage down. Another is pulse width. And then the last is, if you're doing a multi-pulse waveform, the spacing between each individual one. And we're going to talk about, throughout the course of this presentation, how to optimize each one of these three individually as well as automatically. So the first step in waveform optimization is to define the goal of what isn't, and if there are, how big and how many is acceptable for your application. The volume of the main drop, the velocity of that main drop, how far you're going to be spacing your print head and your substrate and how far that drop needs to travel, and then the resolution / speed / jetting frequency. So all of these things are important to know before you start optimizing your waveform so that you know what you're trying to accomplish. So as a simple kind of example of why this is important, so here's a test of which waveform is better. So we've got two different waveforms here with the same ink, waveform A and waveform B. Both of them are viewed with the dropwatcher. Now, from a dropwatching perspective, without any idea of a certain target in mind, you might think that waveform A is better. The drop formation is better. There's no satellites, which you see down here. And so without a clear target, you might be inclined to think that waveform A is the one that you want to develop based on. When you go down the road and actually print, it tells a little bit different of a story. So here's that same waveform on an actual print. So this is a print of one single line. And then here's waveform B. So from a printing perspective, it seems much more clear that waveform B is better. So the idea is between drop watching and printing, we have to have an idea of what targets we're looking for. There were more satellites in waveform B, but that level of satellites was acceptable compared to the higher velocity. And that's the type of information that we're looking for here. So this leads to our next point, which is inkjet printing is more than just jetting. So you need the drop watcher for doing some aspect of it, but at some point you do have to print to be able to set these targets. That's what I just said. So what we have, and it's in our booth at the front of the trade show there, is what we call our print station, which is one machine that allows you to do both of these tests. So you can jet and do your drop watching on one side, and you can also do sample printing so that it can help you determine what these targets are based on the actual results of the print. Here's just a quick little video showing how that works. So you've got the print head, drive electronics, ink supply, everything that's being moved from the drop watching to the sample printing side and back and forth as many times as needed. And this helps you get a much better understanding of the whole aspect of Inkjet, not just drop watching, not just printing, but putting everything together. Something we also have at the front that I just wanted to mention real quick is our new roll-to-roll attachment. So this is a vacuum conveyor belt that's feeding, and then we also have a rewinding option at the other end for those who are interested in roll-to-roll. So this is just one of the new things that we've released. Okay, so here's more of the technical stuff now on how to actually do this. So what we did was we took ink and did a variety of different waveforms. So we have some that are slower but better drop formation, some that are much, much quicker, and you can tell the difference in speed. All these images are captured at the same moment in time. So the drops that are closer to the print head are moving more slowly, the ones that are farther away are moving more quickly. So we've got a whole variety of waveforms here with varying speeds, sizes, and levels of satellites. We then take each of these individual waveforms and actually print an image using it, keeping all other parameters exactly the same. And that's what we've done here. So we've taken our slow, good drop formation, printed an image, our middle, so a little bit faster, potentially more satellite chances, and then we've got our fast and satellite-filled waveform is acceptable. We measure the raggedness of the lines, which is how straight they are versus this kind of jagged edge, how wide the lines are compared to what we want. You can look at color bleed. So this is measuring the spread of the drops once it's hit the substrate, which is dependent on number of satellites and speed. There's just a couple of the variables. And then also the dots themselves. So you can see what dots that are trailed with satellites might look like compared to drops that don't have any satellites. And so the idea is with all of this information, you're trying to figure out what is the ideal waveform that we're going to shoot for when we're trying to do this optimization. Another thing to take into consideration, which is why I threw it in here, is missing jets. Obviously, the waveform is not much good for you if it's not going to lead to consistent jetting over time. So that's another consideration to take in. All of this can be measured with numbers rather than just looking at it with your eye or with a microscope, for example. So here's one of the inspection systems that can accomplish this. You simply put the printed substrate on a scanner, which operates just like the one you would see at home or in the office. The image is loaded into the software and then actually measured. It's measuring the width of the lines, the spread, the dots, all sorts of information. Here's another example of such a system. This is a higher resolution system. So if you want to look at each individual drop, you would do something like this. And these are just to give you an idea of what something like that would look like. So now we'll get into kind of the nitty-gritty on how to design a waveform itself and the process that you would go through now that you have your target of what you want for speed, number of satellites, volume, etc. So most print head manufacturers, when they sell you the head, they have some sort of recommended waveform that it might outline in the user manual or is just a general common knowledge. And so as a starting point for any waveform optimization, it's wise to use that default waveform. And once again, just as a reminder from the beginning, the three parameters that we're really focusing on for optimization is this amplitude, the pulse width, and then the spacing between the pulses. So we're going to take that default waveform that the manufacturer has given us, and we're going to decrease the voltage until we get a nice drop that doesn't have any satellites. It's probably going to be too slow for your particular application in this case, but this is where we want to start for optimization. So here's an example of measuring a drop that's 2.4 picoliters in size and 4.9 meters per second. And this is just the default manufacturer's waveform. The next step is going to involve optimizing the pulse width. So Inkjet, general Inkjet principles say that there's going to be a nearly quadratic relationship between the pulse width of a given pulse of the waveform and the resulting drop volume and velocity, when you jet with that waveform. So here's an example with numbers of what that would look like, but we also have a example coming up with an actual picture so you can see what this looks like. So simply we're just going to sweep through a range of different pulse widths and find which one gives us the maximum volume and velocity. That will be our optimal one for the time being. So here's an example with that same ink that we started with, where the left side is the lowest pulse width, and we just created a bunch of different waveforms just by varying that same moment in time. So remember, if the farther the drop is from the nozzle plate, which is up here, the faster that drop is going. What we're looking for here is where is the maximum velocity of this drop here. And so we can find approximately the pulse width where this occurs. So that's going to be our optimal pulse width for this given ink and waveform. Now that we've done the pulse width, we move on to that next parameter that we're looking for, which is going to be the voltage, or the amplitude of that pulse. There's a linear relationship up to some extent between the voltage and amplitude of these pulses and the drop volume and velocity. So just like we did with pulse width, we're going to sweep through various different waveforms of amplitudes and see which one has the velocity we're looking for as well as the number of satellites that we're looking for. So here's that example. So we took our optimal pulse width that we discovered before, and all we did was simply increase the voltage from one picture to the next. And you can see that the speed seems to increase linearly. And we also notice that towards the higher end of this, the number of satellites is also increasing. As we learned at the beginning, satellites are not necessarily a bad thing. Sometimes the increased speed outweighs the negatives of the satellites. So with those targets in mind that we had before, we're going to choose somewhere along this line where the voltage is that most closely matches that target. So just to give you an example of how much the drop formation can change, just with two simple changes to the waveform. With the optimized pulse width and then the voltage change that we made, there was hardly any change to the drop volume, but we added 2 meters per second to the velocity without changing really any other parameter. So this allows us to potentially jet with the printhead farther away and all sorts of other helpful benefits just from changing the waveform alone. Once we've created our waveform for this one particular speed, it's also valuable to make sure that it will work regardless of what speed you're printing at. So the next step is often to sweep through a range of jetting frequencies to ensure that the jetting looks consistent across all of them. So here's our example here. So in this case, we've got the same waveform every single time, but we're changing our firing frequency from 1 kilohertz up to 30 kilohertz. What we're looking for is the drop volume, velocity, number of satellites, etc., consistent across this entire range. If it's consistent here, that's a good indication that when we're printing, regardless of speed, we should get similar results. If the results are not good, we got to try a little bit lower of a voltage. And here's an example of results that would not be good. So as you can see, as you increase the frequency, there reaches a certain point where the speed of the drop drastically increases, along with the number of satellites and all sorts of signs that the jetting is a little bit out of control, and then it seems to return back to normal at frequencies beyond that. So this is a good example of what resonance looks like inside a printhead. So as the ink is moving back and forth, being jetted, being refilled, there's some residual acoustic waves that are going on inside the head. And if we get our frequency just right, which is what's going on here, the waves are building upon each other with every single drop, and we're hitting some sort of resonance frequency. So if you're seeing something like this occur, where the print doesn't look good at certain speeds, but looks good at all the others, it could be something like this that's going on. If you are happy with the drops or faster drops, you might need to add a second pulse to create some more momentum. And that's what we're going to talk about here, which is commonly known as grayscale printing. So the spacing between the pulses, this distance, is also very important. As I've mentioned how the drops are moving back and forth within the nozzle plate, you want to make sure that you're adding momentum at the right time. You don't want to be working against the acoustics inside the head. You want to be adding to them. And here's kind of a diagram of what's going on here. So this is the pressure within the head, and as it's filling and jetting, the pressure is going in one way or the other. We want to find the appropriate spacing between the pulses to make sure that we're adding to the pressure rather than detracting from it. And that's what's known as acoustic time, and that's what we're trying to find here with this next step. So we simply, in this image, are varying the spacing between the two pulses, and the optimal spacing, or the acoustic time, is going to be when the speed of the second drop is the fastest, because that's going to tell us we're building on it to its maximum potential. So we can see here that the speed of this found knowledge to get bigger and bigger drops as needed. Something else that is a new feature of our product that kind of comes into play here is we've modified the ImageXpert system so that it's able to look more at the nozzle directly. This is helpful as you're optimizing the waveform, because if you see in between every drop that's actually being ejected, there's a little meniscus of activation there. And so this is a helpful tool for being able to create a tickle pulse or optimize the waveform, or if you have a problem with wetting that you might not necessarily be able to explain, something like this could possibly help explain that. And that's a new feature that makes sense to mention at that time. So we've created all our pulses, and we're going to we've got this newly found optimal timing, and as long as we keep all of our pulse spacing consistent with that same acoustic time, our waveform will look pretty good. Obviously, each print head has its own nuances to it, so the precise approach is going to be print head dependent. But in general, this is the concept that we're going to be working with. Then as needed, we can make small adjustments from there. And this is where waveform optimization kind of walks the line between an art and a science. So up to this point, it's been science, and now at this point, it's a little bit of experience and art and experimentation. So we've been walking through the process very quickly, but in practicality, this can take a very, very long time to try to test all of these things manually. So the good news is that this doesn't have to take forever. There's an automatic way to do that. And we've got this set up at the beginning, at the front of the show, I mean. We've got the ability to load all the different values that we want to test for a particular variable. So we're testing all of this range of pulse widths, for example. Could be voltages, could be frequencies. And the system is automatically going to apply those different ones to the waveform and then capture the volume and the velocity of the drop at each one of those steps. And as it works its way through the list, you'll be able to see exactly like what we were showing before, where we're looking for the drop with the optimum velocity. With these numbers, and as we're stepping through these different waveforms, it'll quickly become clear which one is optimal, and that'll happen in just about a second here. So as a reminder, this is all being done automatically right now. And down here we've got the pulse width, and we've got the drop velocity. And what we're looking to see is where is the drop volume and velocity maximized. If you remember from the beginning, we said that pulse width tends to have a quadratic relationship with volume and velocity. And so it looks to be so far consistent with the theory. And the theory is that our optimum pulse width would be this value here. So at this point, if anybody has any questions, thank you for your time. And if you have any questions, I'm happy to answer them now, or we can address them at our booth in the front. So thank you.